In this video tutorial, we'll be continuing from the last video in this series and looking at how we can add displacement or animated deformation to our Raymarched sphere. We'll also take a look at how we can start drawing different kinds of signed distance field shapes, as well as how to use functions in HLSL inside the custom node in Unreal 5. To begin, we'll be using the exact same setup we had in the previous video. So that code that we currently have that creates our Raymarched sphere will be continuing from that. So we should have something similar to this where we have our custom node with our code from the last video, and then all our connections defining the sphere radius, the light position, and so on. So our code should look something like this. And I'm just going to use Visual Studio Code so you can see the syntax highlighting and the code a little bit easier. Now we've already defined our sphere. So this is our signed distance field for the sphere. And then here we calculate the surface normals, the diffuse, the reflection, and everything else that we need to draw this properly with highlights and all. So what we're going to want to do is change the signed distance field. This is currently what defines our sphere shape. And what we're going to want to do is modify this. To make this a little bit easier to deal with, we're going to leave this as our distance field, and we're going to add a new variable. And that new variable we're going to call displace. And we're going to make it equal the sphere center. So what we can kind of do right now is take this sphere center here and remove that and replace that with our displace variable. And what this will do is make it easier to just modify that additional wobble or deformation we're going to be adding onto the sphere. So now we have sphere center defined here as this displace variable, and we've replaced it from here. What we're going to do instead is we're going to take that sphere center and we're going to plus, and we're going to add some wobble on top of it. So we're going to use a sine curve, and inside that sine curve we will use the ray origin, and we'll use ray origin x multiplied by sine time divided by 3. And then we're going to do that and plus, and kind of repeat this. And I can really just copy and paste this. So if I take a look at this, we have our open bracket, close bracket, and our final close bracket. So I'm just going to copy this, and I will paste that again, and one more time. And then I'll close that bracket. So we're going to do this for X, Y, and Z. Something like that. So we'll take our sphere center, and then what we're going to be doing is adding this sine curve with our ray origin X, Y, Z multiplied by sine time divided by 3. And that's going to give us some wobble or ripple into that shape. So once we've done that, if we take all this new code with this displace variable now, we can copy this, and I'll go back into Unreal and just paste this as the new code that we have. We'll notice that when it compiles, we'll get an error because we don't have time defined. So I'll have to go in here and add a input and call that input time and connect it to time. So now what we see is we get a ripple, which is pretty cool. The only problem that we might notice here is that our highlight might not properly react with that deformation now. So one thing we should also check in our code, and I'm just going to go back to Visual Studio, is that what we have when we define the surface normal is ray origin minus sphere center. But technically it should be minus displace. Because if we use sphere center, it won't be having the correct shape. Whereas if we use displace, it will use sphere center plus all this deformation that we're doing. So we want to make sure that we're having the normal of the correct shape. Currently, with that just being ray origin minus sphere center, we would have the normals and light interaction with that surface for our highlights as if it was just a sphere, even though it's being deformed. So having this properly updated to be the proper normal or surface normals of that new shape will give us better interaction with that highlight. That highlight will react properly. So that's one thing we have to be aware of. Otherwise, you're not going to get the best result and things won't look correct. So we'll make sure we have that done as well. And now everything should be updated. And if we take this code and one more time, just update it here, we'll now get proper highlight. Might not notice too much here from what it was before, but now we know that everything will be correct. And if we save this and we view it in our viewport, this is all looking as we'd expect. And this is pretty cool. Like if we take a look at this, it feels like a 3D sphere with some animated displacement. But again, may I remind us, it actually is a cube and it just has this material on it that is pretty much emulating the drawing of a sphere. So if we want to create more complex things, we're going to have to probably start using functions in our HLSL code. And this is something you might be familiar with if you've done coding before, where you think, hey, I know how to do a function in Python. I know how to do a function in some other programming language. That's going to be pretty easy. It is, but using the custom nodes in Unreal do pose a little bit of a problem. If I go in here and I just create a material and I just call it like simple function, I'm just going to open it up and we're just going to go in here and just to create an example here right now. Nothing really important. I'm just going to create a custom node. I'm going to put that into emissive color and we're going to make it output red. So normally if we want to do that, we could just do something like return one for, or I guess return float 3, 1 for red, 0 for green, 0 for blue. That's it. And yay, we get red. Now, if we want to make a function that does that, totally useless, but let's just see. If we want to make a function, how do we do a function? And maybe I'll type this into Visual Studio Code just so you could see it a little bit easier. And if we want to do a very simple function, we'd probably want to do something like this. We'd do like float 3, color choose. If we want to choose a color, we'd allow an input for the red color. So int for integer. So it's just like solid numbers. Int red, int green, int blue. Doesn't really matter. Just as an example. And then open up that function and we would return red, green, blue. So it'd be a function that takes 3 values, red, green, blue, and it just returns that as a float 3 for your color. So that's like a simple function. And if we want to go take this and try this out in Unreal, like maybe we'd have to also return our function here. So we'd have to do something like return color choose 1, 0, 0. Okay, so that should all be good. Like that should definitely work. Now if we copy that and we go to Unreal and we paste that in here to our custom node, okay, we get a bunch of errors. And the errors say, right down here we can see error function definition is not allowed here. It's not the greatest error, so why can't we use a function in our HLSL code? And this is something that we have to be aware of when using these custom nodes. Eventually we could type our code into an external file and kind of reference it in here, but for now, if we wanted to do a function inside one of these custom nodes, we're going to run into this problem. So how do we get around this issue? we have to put our function into a structure. So what we could do if we wanted this to properly work is we could define a structure. So I'm going to do struct color operations. You call it whatever you want, but I'm just going to call it color operations for this. And I'll open that structure, put this function inside, close that structure, give that structure a name that we can reference to. So color operations CO. And then if I want to use that function inside that structure, I would do something like return CO dot color choose, and then red 1, green 0, blue 0. And that should work. So if I were to take this now, copy that, go back into Unreal, paste that as the new code, hit enter, hey, that now all works, no problems. So if you put your functions into a structure, you're going to be able to use them within your custom node. So now that we know how to use functions and properly get that working, we're going to go back to our other code where we have our wobbly sphere, and we're going to modify this code to not draw a sphere anymore, but to draw something like maybe a donut shape or a torus shape. So this is our code that we currently have. And what we're going to do a little bit different here is we're going to make a structure with a function. So I'm going to make a new structure called struct SDF, sign distance field, shapes. And maybe we can add a bunch of functions in here, draw different shapes. But for now, we're just going to add a donut or a torus shape. So the function is going to be a float that will return. It's going to be called donut. And we're going to make it float 3. So P is going to be the variable, and that's going to be for our ray origin. And then float size for the size of the donut. And then float cutout for the cutout, the hole in the center. So we're going to do that. And inside this function, what we'll do is we'll do something like float 2, so 2 values. We'll call it Q. And what we're going to do here is define the size pretty much. So we're going to do length p.xz minus size, and then p.y. And then we're going to return the length of this Q variable, and then minus our cutout, the center of that donut shape. And that's going to be our full function to create the sign distance field of a donut shape or a torus shape. And then I'll wrap up this structure. So I'll just go in here and call it SDF shapes, give it a name, call it SDF. So I can just refer to that donut shape as SDF.donut. And then if I want to add this into my actual code here and replace our wobbly sphere, I'm just going to remove that displace code that we did. This is going to be distance or dist equals sdf.donut ray origin. Size of the donut, let's do like 50, the cutout in the center, maybe half that, 25. And that's it. So it makes it actually a lot simpler when I look at it now. We have our donut function up here, and then we can just easily use it and fill in the information we need, the ray origin, and then size, and then cutout. So that's really it. And if I copy this code now and go back into Unreal, paste it to update here, what do we get? Well, we get an error. Oh, I didn't remove displace. So I'm just going to go back to the code here. We still have displace down here. Instead, it's just going to be minus. And then this is something interesting. We need to calculate new surface normals. For now, I'm just going to make this a value of 0. It's going to make the shape look totally messed up, but we'll talk about that next. I just want to make sure that we actually get this donut shape to show up. So for now, I'm just going to break the normal. I'll make it equal 0 just to see if this all works. So let's update this code. Okay, so what do we got? Awesome, we got our donut shape. Now you can see the shading and the highlighting is totally broken because we haven't defined any surface normals. But there we go, we have our donut shape. So really easily done. Now how can we get this surface normals updated? For something like a sphere, it's fairly easy. For something like a donut like this, it gets a little bit more complicated. So how are we going to deal with that? Well, I'm going to go back to the code here. And what we're going to do for the normal, I'll give myself a bit of room here. For the normal, we're going to make it equal normalize float3. Now for the surface normals of a donut-like shape or a torus, we're going to pretty much have to do 3 things, x, y, z, and we're going to pretty much have to calculate the surface normal at the intersection point of the ray and the SDF. So the easiest way we can do this, while keeping this in one line, technically we could make a function that just calculates the surface normal, but that'll get a little bit more complicated. So to keep this fairly simple, I'm going to use our function. And this is why it's important to be able to have functions. If we didn't have that function, this code would be much, much longer because I'd have to keep retyping all this out and it would just start to balloon to become a lot more code than it really should. So since I have that function out, I can utilize it to calculate these surface normals. So I can do something like SDF.donut and then float3, fill in the function. So ray origin. But what I'm going to do is ray origin x plus EPS. Now what's EPS? We haven't defined it yet. What this EPS variable will be is like a little bit of a precision buffer almost, or an approximation value to give a bit of a buffer to avoid floating point errors and problems. So I'm going to define this variable here called EPS. So I could just put it here or anywhere really, float EPS, and let's make it like a very low number. Something like that should be fine. And it just acts as like a bit of a buffer, like a kind of a way of adding a bit of flexibility to the precision to avoid problems. And then we're going to do ray origin y, ray origin z. And then what we're going to do is the size of the donut, so 50, the cutout 25. And then after that, I'm going to minus, so I'll go here to the next line to try to keep this easy to look at. I'll do minus SDF dot donut, again using that function again, float3 ray origin dot x minus EPS, ray origin dot y, ray origin dot z, and again 50, 25. And then again, we'll kind of repeat this. So we'll do this, and technically I could probably just copy and paste this. So what I'm going to do now, since I have this, is I can go back here. It's going to take all this all the way up to here, and I will pretty much, actually all the way back here, pretty much be able to take this again and again 3 times, and it will be x, okay, and then y, x, okay, so that's all good. And then z, what we're going to want to do here is also add plus EPS, And then here, for y, we'll do minus EPS. And then here, we'll do plus EPS, minus EPS. To make sure we have this all properly filled in. So I'm just going to check through this. And this does get a little bit complicated, but this is pretty much just manually defining the surface normal with our function. There are better ways of calculating this, but this is just to keep things simple for now, in the sense that we're not going to have to make a whole new function just to figure out our surface normals for this shape. So we have pretty much our normalize, and then we have float 3. So we have our 3 values here, x, y, and z. And we are calculating all these surface normals. So this looks like it all works good. So we have y and plus EPS for x, plus EPS for y, plus EPS for z. So that's all good. Best way to check this out and see if it works, copy it, and let's put it into Unreal. So I'm going to go in here, paste it in. Let's see if our surface normal works. Okay, so it looks like there's something a little bit off here with how that highlight's working. So I'm just going to take a double look at this and make sure we're not missing anything. So this all looks good. And then we have our XYZ. And then we have our XYZ and minus. Here we go. Don't want that. Because we already did that here, X. Now it should be Y. Okay. And then for Z, don't need this here. So copy and pasting can sometimes get you into a little bit of trouble. And then here it wouldn't be X minus, it would be Z minus EPS. So we're kind of just, for X, which is here, we do ray origin X plus EPS, and then we minus ray origin X minus EPS here. And then we do that here for Y, so then here it's no longer X, we shouldn't have that plus here. It then becomes Y plus EPS, Y minus EPS, and then finally for Z, Z plus EPS, and Z minus EPS. So that's all good. And now we copy all this, put that into Unreal. That's going to give us correct surface normals. Look at that. Now the highlight is working as I'd expect for this kind of shape. Feels a little bit more correct. So if we save that now, and we test this out in our viewport, here's our donut-like shape. Let me take that sunlight and just rotate it. Pretty cool. All seems to be working. So now we have our donut-like shape all done in Unreal. And again, this is really just a cube, but our Raymarching is creating the shape with a sign distance field, and we've updated all the surface normals to work with that, and we're using a function in our HLSL custom node in Unreal to create this shape and to help calculate the surface normals. So it's pretty awesome that we're able to do this now, and we've definitely taken a big step forward into starting to build a little bit more kind of heavy code here. This is starting to become quite a bit, but you can start to see how we can start to make shapes and use these functions and build up more complex things. So hopefully this has helped out kind of get a better understanding of how we can make and start making more of these types of shapes and start using functions in Unreal and custom nodes. If you found this video useful, please like, subscribe, and if you're part of the Patreon, you will get also access to the PDF that goes over all these steps in a little bit more detail. And in the next video, what are we going to be heading on to? We're going to start taking a little bit of a step back, moving away from these signed distance fields and shapes, and we're going to start looking at how we can start loading in custom textures and Raymarching them in depth. So taking our own textures and giving them the illusion of depth, or duplicating them in slices in distance or in 3D space. So that's what we're going to start taking a look at in the next video.